We're going to connect the idea of molecular orbital theory with this aromaticity concept. And this is why I went over molecular orbital theory last chapter. I wanted to refresh your guys' memories on what it was. And so molecular orbital theory allows us to see if molecules are aromatic or not. So to begin with, we have to look at the benzene ring, and we have to ask ourselves how many electrons are in the pi orbitals, or the pi bonds. Okay, so there's 6 pi electrons. Okay, and then we're going to look at how many p orbitals there are, and so there is going to be 6 p orbitals within this molecule. Okay, and they're the ones that are allowing the 6 pi electrons to delocalize throughout the ring. So to draw the MO for this, we just focus on these p orbitals. And so we're going to draw 1, 2, 3, 4, 5, 6. And we put in 6 electrons. And these are our atomic orbitals. Okay, and now we're going to put this into a molecular orbital. And the unique thing about this is that the shape of the ring is actually going to be the same shape that the MO orbitals take in the energy diagram. So we have right here, there is a orbital, there's 2 orbitals there, okay, and then there's 2 orbitals here, and there is an orbital there. And so what you're going to see is if you connected the dots or connected these lines, it would look like the cyclohexane that we've drawn for the aromatic ring. So what we have to do is we have to identify bonding and anti-bonding. So anything below the line is bonding, and anything above the line is anti-bonding. Okay, and so for a molecule to be aromatic, all of its bonding orbitals need to be filled, and there needs to be no electrons in the anti-bonding or the non-bonding region. And if it was non-bonding, it would be exactly in line with this dotted line I've drawn. So you don't want electrons there. We don't have orbitals in the non-bonding in this specific orbital or MO diagram, but just pointing that out for now. So I have 6 electrons that I need to fill into my MO diagram. And so I'm going to start at the lowest energy, and I filled in 2. And then I'm going to go to the next level. And remember, fill in single spins at the same level, and then backfill. So there's 4, 5, and 6. Okay, so what we see is that the MO diagram, we have all of our bonding orbitals filled, and we have nothing else filled. There's no electrons. Even if there's a single electron in the anti-bonding, it would be not aromatic. And so we can say that this benzene molecule is aromatic because of that. Okay, now let's look at a different molecule. Okay, this molecule may look weird because it's a charged molecule with a carbanion in a location on the ring. But we are trying to assess if this molecule is aromatic or not. And when we look at it, we can say that there is 6 pi electrons in this molecule. The negative charge and those lone pairs that are making that negative charge are sitting in a p orbital. And so if you count everything up, it allows resonance to happen, and it would be part of the pi orbital systems. And that's going to make 6 pi electrons with the other 2 double bonds. Now we're going to ask ourselves how many p orbitals are there, and there are 5 p orbitals. Okay, so we're going to fill those in, or draw those in. 1, 2, 3, 4, 5. And then we're going to fill in with the electrons, and that's 1, 2, 3, 4, 5, and 6. Okay, now again, I've told you that the shape of the molecule is going to be represented in the MO diagram. To do this correctly, make sure that the point is on the lowest end. So we're going to turn this molecule around and the point is going to be down. So there we go, there's our bottom. Then we have the two shoulders and then the other two higher up. So if you were to draw lines from these, if you were to connect all these lines, it would take the same shape as our cyclopentane molecule above. Now we have to fill in. Okay, so first we designate what's bonding and what's anti-bonding. So anything below this line is bonding, and anything above is anti-bonding. Okay, so remember, we want to fill in all the bonding, and we don't want any electrons in the anti-bonding orbitals. Let's see what happens. 2, 4, and 6. I've used up all the electrons. All my bonding are filled, and there is no electrons in my anti-bonding. So we can conclude that this odd-looking molecule with the carbanion in it is aromatic. Okay, and if you were to run simulations and calculations on this type of molecule, you would find that it has an odd stability to it, and it's because of this aromatic property. So this is how we're connecting the MO theory. This is why we went over it in the last chapter, and so we're showing how to use MO theory to help us discover if a molecule is aromatic or not.